So in this video, we're going to look at an example that's relevant to the content that we covered in Learning Module 5 or the previous video. I'm also going to give you a bit of a preview of one of the questions that I'm going to ask you on this manual first homework. So what we're trying to do here is we're given a visual description of a vector in three-dimensional space. And what you're going to find by the time you're done with this long sequence, whether you take statics here and dynamics somewhere else, or whether you move through the entire thing with us through next semester, is that oftentimes one of the most challenging things of the problems in this book is trying to actually understand what the drawing is intended to mean. So unfortunately, this is a pretty easy one, but that it will become more complicated as they actually try to incorporate additional physical things into their drawings. But we have some type of eye hook here, and there's a force that is exerted on it. It's 100 pounds in magnitude, and relative to the coordinate system which they've established, not surprisingly, they've aligned the planar coordinate system with the kind of hook itself. And the z-coordinate, of course, follows a right-handed rule. It's positive kind of coming out of the surface of the ground here. We're asked to express f as a Cartesian vector. So the first question is, what do they mean even by Cartesian vector? Cartesian vector is just another fancy way to say to decompose a vector into its rectangular components. So we want to break it down into I hat, j hat, and k hat components. So you notice here, again, take the engineering approach, say, hey, I don't really know how I would do this. However, if it wasn't kind of pointing in three-dimensional space, if it instead it was in the XY plane, well, that's just like the example that we did last week and earlier in the week in our lecture. So the question is, how can I actually get it down and reduce it to a problem where this is just a vector lying in the XY plane? So notice I can form a right triangle, which consists of which side lengths? Well, the hypotenuse is the vector itself. There would also be a base, so this is kind of the light shaded right triangle, which is drawn. One of the bases of the triangle would also be drawn vertically, and notice that it'll be perfectly parallel along the z-axis. And the second base will be only in the XY plane. And you might remember that we called this base, and again, I'm talking about the light blue triangle here. This space is known as a projection of this vector into the XY plane, and this space is nothing more than a z component. So viewing that, just breaking it down as a triangle, that's a triangle with a hypotenuse. And remember, one of the confusing things about statics is you're like, hey, how when I draw this triangle is this length 100 pounds? Well, that's one of the big ideals here is don't worry about the units for the time being. Just call that hypotenuse 100 units, whatever it is. So if there were 100 units of force along the hypotenuse, if you were to decompose it into a component which was perfectly vertical or aligned with the z-axis, and one of which was in the xy plane, you could use your right triangle trigonometry and notice that this 60-degree angle, the z component, is opposite of that angle. So naturally, the sine of 60 degrees is going to be this side length, remember SOHCAHTOA, divided by the hypotenuse. What that means is you can compute this side length as the hypotenuse times the sine of 60. So decomposing this 100-pound force, we can find an equivalent component in the vertical direction by taking 100 times the sine of 60. In a similar fashion, if we take 100 times the cosine of 60, since SOHCAHTOA means adjacent over hypotenuse, we'll notice that that side length is the projection and lies perfectly in the xy plane. So this is usually the way these problems work. Take it and break it down into a component that you need and a projection component that will allow you to find the other two components that you need. So here we're going to use the 60-degree angle. We'll use 100 times sine of 60 to find the z component. We'll use 100 times cosine 60 to break this down into the x and y plane. Now notice once you have this projection broken down into the x and y plane, that you naturally have a right triangle where the two bases are the x component and the y component. Here's your right angle, and this interior angle, 45 degrees, is one of the angles that we were given. Now, the fortunate thing about the 45-degree angle is even if you were to mess up and not use sine and cosine incorrectly, since they're the same, you'll get the right answer, but we don't want to rely on that. Notice in this darker blue triangle, the hypotenuse is that projection that we computed, 100 times the cosine of 60, and whatever that is, it's just some number. We can get, relative to this 45-degree angle, the x component is adjacent. So cos 45 is going to be equal to the ratio of the x component divided by the hypotenuse. Alternatively, I can get the x component as just taking this hypotenuse and multiplying by cos 45. And I can get the y component by taking the hypotenuse and multiplying by the sine of 45. Now, the one thing you have to be careful when you're doing these problems is if you just treat them as triangles and their side lengths and you're not really thinking about sines, you have to manually adjust the signs after the fact. And that's the only trick in this problem. If anyone were to miss it, if I were to give you a homework question, that's likely how you would miss it. So after you do all of that, just go back and make sure that you don't need to make any manual sign adjustments. So clearly, when we computed the magnitude of the z component, we're fortunate that if we were to decompose this vector using the triangle rule, that the z component is going to point in the positive z direction. So that's good. Notice that in a similar fashion, when you have that decomposition in the xy plane, the x component kind of points along positive x. However, the y component points along negative x. So that's why I have this negative sign here. The reason I'm using fxy here, technically, of course, fxy is f cosine 60, as I've shown above. It just keeps the math a little bit shorter than showing the two trig functions right after one another. And once you compute all these numbers, you just put them together in whatever form you like to write it. You can write it as a number times I hat plus a number times j hat plus a number times k hat, or alternatively, you can just put them within angled brackets as we talked about in the last lecture. So on the first homework, I'm going to give you a problem that kind of involves this. You have this pipe assembly. You have linear dimensions of various components of the pipe assembly. However, down here, we have a force that's acting upon the end. And if you notice, we're given two different vectors. We're given a 30-degree two different angles, I should say. We're given a 30-degree angle, which is kind of in the plane of the vector itself and the z component. Just be careful with your sign on that one. So from this 30-degree angle, you're going to be capable of decomposing this into the kind of a plane which is aligned along the xy plane. And then that 40-degree angle will allow you to decompose the x and the y components. So hopefully that question goes well for you. If anything goes bad, again, I bet it will either be the actual being able to see the image itself, because unfortunately, we're going to be limited by the resolution of the images, or just not being able, even if you can see it, not being able to interpret what the angles are actually describing on the picture. So it's a little bit of an art, and we'll get more into it as we move throughout the course.